This is the week 7 lecture assignment problem solution session. So in the last session I had some problems, so I could not join for the live session. That live session postponed to today. So I will explain in the extra session. I just explain some of the basic concept of Laplace transform and its properties and its application, and I solved some of the numericals. So here today I will briefly discuss about the Dirac delta functions, its properties and application. Then I will solve the problems of assignment number 7. So let's start with some basic concept of Dirac delta function. So the Dirac delta function has a numerous application in physics, mathematics. So basically we know the various uses of Dirac delta function in the context of electrodynamics. So here we will look at the role of the Dirac delta function within the theory of differential equations. Before that, we will recall what is Dirac delta functions. Let's start with what is Dirac delta function. So technically speaking, the Dirac delta function is not really a function, but it's called a generalized function or a distribution. However, we will simply learn how to work with its properties with the help of many examples. So let's consider a Gaussian function. So the Gaussian function is given as f of x is equal to 1 by root over of 2 pi sigma e power minus x square by 2 sigma square. So if we plot this function, so this function will look like, if we plot this function will look like this. So we see that if this sigma, if we reduce this sigma, this peak will be increased. If we reduce the sigma, this peak will increase. So the peak become larger and larger for the reduced sigma. So this happens in a very precise way, such that the area under this curve is always unit. That means if you start with a Gaussian distribution function like this, so the area under this curve is always unity. That means if you reduce the sigma, the peak will increase, but the area remains same. So next, if we do that, the area remains unit means the integral of, let's say, 2 pi sigma minus infinity to infinity dx e power minus x square by 2 sigma square equal to 1. So regardless the value of sigma, this sequence of functions goes to the Dirac delta function when sigma tends to 0. So the function itself takes an infinity value at x equal to 0, so and 0 everywhere else. So its width is 0, thus it is a weird kind of functions. the key property though it's that are under the curve remains unity. We denote that Dirac delta function centered at a point at A by delta x minus A. That means it's 0 everywhere except at x equal to A. So it becomes infinite in precise controlled way such that it satisfies two key properties. That means the two key properties are integration minus infinity to infinity delta of x minus A dx equal to 1, and delta of minus integration of minus infinity to infinity any function gx delta of x minus A dx is equal to g at ga. So for any arbitrary function of gx, thus we see that the Dirac delta function is best handled by integrating out. It can help pick out the value of a function at certain point. We will see how later this property is useful. So we build off the Dirac delta function considering a sequence of Gaussian functions. The same Dirac delta function could have been obtained using many other sequences. Let us look at just one another. So let f of x is n e power minus nx where x greater than 0 and 0 for x less than 0. So this, if we plot this function, we will get the plot like this. So it can be shown that this sequence 2 in the limit of n tends to infinity goes to the Dirac delta function. This can be verified with the key integral properties. So let's dive into another concept. So the Laplace transform of Dirac delta function. So the Laplace transform of Dirac delta function, let's say d del t minus t0 is equal to, from the definition of Laplace transform we know that the Laplace transform of any function is given as the function multiplied with e power minus st integrated over dt from limit 0 to infinity. So using the properties of Dirac delta function, so it is e power minus st0 for t0 greater than 0. So we can use this property to solve the differential equations where an external force field is applied which is impulsive in nature. So the delta function is used to model the situation where an impulsive force acts. So let's look an example. So given d square x by dt square plus omega square x is equal to delta t minus t0. So suppose the initial condition is given x at t equal to 0 is 0 and dx by dt at t equal to 0 is 0. So let's do the Laplace transform of this differential equation in both sides. So Laplace transform of d square x by dt square plus Laplace transform of omega square x is equal to Laplace transform of delta t minus t0. So if we apply the formula for Laplace transform of second derivative of this, so we'll get square xs using the formula for Laplace transform of derivatives. So we'll get minus s square xs minus sx at 0, then del x by dx by dt at 0. So we will get x square xs, because after substituting the limit, the initial conditions, we will get this. So if we substitute this into this equation number 1, we will get x square s x plus omega square, and the Laplace transform of x is, let's say, xs is equal to right hand side, it's become e power minus s t0. So xs is equal to e power minus s t0 by x square plus omega square. So now you can, in the previous session, I just wrote it down, the Laplace transform and its function and its Laplace transform. If we look at this table, we can get the, if we do the inverse Laplace transform of this, so we will get, you can just check, we will get at 1 by omega theta t0 t sine t minus sine omega t minus t0. So this side is explicitly can be written as x at t equal to 0 for t less than t0, 1 by omega sine omega t minus t0 for t greater than t0. So next we will see the Fourier transform of Dirac-Delta function. Fourier transform of Dirac-Delta function. So just like the Laplace transform, the Fourier transform of the Dirac-Delta functions has too many applications. So let's look at an example. Fourier transform of the Dirac delta function is 1 by 2 pi integration from minus infinity to infinity delta x minus a e power I alpha x dx is equal to 1 by 2 pi e power I alpha a. So if you do the inverse Fourier transform, it's a very useful integral representation of Dirac delta function. So if you do the inverse Fourier transform, then the Dirac delta function is given as delta x minus a is equal to 1 by 2 pi integration from minus infinity to infinity of e power alpha x minus a dx. Of course this integral does not converge, so this is only a formal representations. So the correct way to think of this is to change limit from integration minus infinity to infinity to minus n to n. So as n is increased, we will obtain a sequence of functions that becomes more and more simply picked about a. So this is basically having the area unity, just we seen earlier. So now we will look at some properties of the Dirac delta function. So starting from derivatives of the Dirac delta function. So derivative of Dirac delta function. So given some arbitrary functions, let's arbitrary function phi of x, let's take the integral from minus infinity to infinity phi of x delta prime x minus a dx. So if we do the integration by parts, we have integration from minus infinity to infinity phi x delta x minus a dx. This is equal to phi of x delta of x minus a, limit from minus infinity to infinity minus infinity to infinity delta of x minus a phi prime x dx. That is simply minus phi prime at a. So integrating by parts 2 times, we will get, let's say, minus infinity to infinity phi x delta prime double prime x minus a dx. We will get phi double prime at a. So in fact, on successive integration by parts, generally for nth derivative of the delta function, we will get minus infinity to infinity phi of x delta of n x minus a dx is equal to minus 1 to the power n phi of n a. So other properties of Dirac delta function, let us recall the Laplace transform of the step function. Let Laplace transform of step function at ut0 t is equal to e power minus s t0 by s, where t0 is greater than 0. So the Laplace transform of derivative of the function is, let's say, ut0 prime t is equal to s into e power minus s t0 by s minus 0 is equal to e power minus s t0. So but we have seen that e power minus s t0 is the Laplace transform of the Dirac delta functions centered about t0. So here u t0 prime t is equal to delta t minus t0. That means this is also a property that we can obtain directly by showing let's say integration from infinite to infinite minus infinite to infinity dt u t0 prime at t f of t is equal to minus infinity to infinity dt delta of t minus t0 f of t is f of t0. So let us look at more several properties of Dirac delta function. So another property is x delta x is equal to 0. So to check this, you can see that minus infinity integration from minus infinity to infinity dx x delta x phi x minus infinity to infinity delta x x phi x delta x is equal to 0. So x dx is equal to 0. So next is x delta prime x is equal to minus delta x. So this is also a property. So let's consider integration from minus infinity to infinity delta x x delta prime x phi x. So that is equal to minus infinity to infinity dx x phi x delta prime x, which is equal to minus phi 0. So this is consistent with x delta prime x is equal to minus delta x. So we could have obtained this result by taking derivative of the previous results. So next properties is delta of minus x is equal to delta x. So to see this, we introduce some test function. Let's say the test function is phi x. So if you do the integration from infinity to minus infinity to plus infinity delta x dx delta of minus x phi x is equal to infinity to minus infinity of minus dx delta x phi of minus x equal to phi 0. So thus delta x is equal to delta of minus x. So next is delta of ax is equal to 1 by mod a delta x for x not equal for a not equal to 0. And next properties is, let's say, delta of x minus a x minus b 1 by a minus b mod delta of x minus a plus delta of x minus b where a is not equal to b. So if we extend this logic in a more general way, so we will get, let's say, another property, delta of f of x is equal to summation over I delta of x minus xi divided by f prime xi mod if f of xi is 0 and f prime at xi is not equal to 0. So these are the properties of Dirac delta function. Now we will see some of the examples of Laplace transform and the Dirac delta function. So let's look at the first problem. It's compute the Laplace transform of the function f of t, which is t when t is in between 0 to 2 and 3 for t greater than 2. So this is, we know, we can do it various ways. So let's see how we can solve this. So we know the Laplace transform formula, that Laplace transform of any function is given as integration from 0 to infinity f of t power minus st dt you can try it. Let's try. So here, as you know, the Laplace transform of any function is written as f of s is equal to f of t 0 to infinity e power minus st dt. So here we can split this function as f of t from 0 to 2, f of t value is t e power minus st dt plus integration from 2 to infinity 3 e power minus st dt. So if you do this integration by parts, so you will got t e power minus st by s from limit 0 to 2 plus 0 to 2 e power minus st by s dt plus this part, you will get 3 e power minus st by s infinity to 2. So for s greater than 0 and limit t tends to infinity, so e power minus st is equal to 0. So f of s is defined only for s is greater than 0. So then the f of s you'll get here, after substituting the limit, you'll get f of s is 1 by s square plus e power minus 2s by s minus e power minus 2s by x square, or s is greater than 0. So you can see that the option number here, option C is correct. So the next, let fs be the Laplace transform of the function f of t is equal to t square cos t. So we have to find f of s at s equal to 1. So we can simply use the formula for the Laplace transform, then we can compute. So here you can see we can use the properties of, let's say, Laplace transform of t to the power n f1 t is equal to minus 1 to the power n dn f1 s by dsn. So it's simply you can use the formula for the Laplace transform, so it's easier to handle with Laplace transform of using various properties also. Then let's see here, t to the power n f1 t, here f1 t is cos t, and t to the power n means here is given t square. So that means we have to differentiate 2 times of the Laplace transform of cos t. So let's find out. So where f1 is, we can find that Laplace transform of f1 t. So here f1t is cos t, so we know the Laplace transform of cos t is s by s square plus 1, where s is greater than 0. So now we'll compute the Laplace transform of t square cos t, which is minus 1 to the power n df1 s by ds. That means here we have to do the 2 times derivative with respect to s. So let's compute it. So it will be minus 1 to the power 2 d square f1 s by dx square, where d by ds of d by ds of s by s square plus 1. So upon the first differentiation, we will get differentiation with respect to s of this function is nothing but 1 minus s square by x square plus 1 square. So here minus 1 to the power 2 is plus 1. So again differentiating this function, we will get just simply differentiation with respect to s, we will get 2s x square minus 3 divided by s square plus 1 to 3 power 3. So it's given, we have to compute f1. So in the place of s we can substitute 1. So we've got the Laplace transform of f of t. Then we have to compute f of s at s equal to 1. So simply just substitute 1 in the place of s. After substitution we will get f of 1 is 1 by 2. So here the option number A is correct. So compute the Laplace transform of the function. The f of x is given as 0, 1, 3 when t is in between 0 to 4, and 1 when, I think there is a typo, this will be 7. Then 3 when t is greater than 7. So we can use Laplace transform formula also here. You can split the integration in 3 different parts. One is limit from 0 to 4, then another limit is 4 to 7, another limit is 7 to infinity. So this is a for this method we can use also. Again we can use a different method using the step function. So here we will see using the step function how we can solve this problem. So let's see, this function f of t can be written as t minus 4 theta 4 t minus t minus 7, so theta 7 t. So we know that theta a t is 0 for t less than a, 1 for t greater than a. So any step function can be written in the combination of step functions. So if we find Laplace transform of the step function multiplied with the function t minus a, we will get e power minus as Laplace transform of f of t. So similarly for Laplace transform of theta a t for t minus a, we will get e power minus as Laplace transform of t, that is equal to e power minus as by s square. So again for f of t is equal to t minus 4 theta 4 t minus t minus 7 theta 7 t. So if we find the Laplace transform of this function, we will get L of t minus 4 theta 4 t minus Laplace transform of t minus 7 theta 7 t. So you can find the Laplace transform in a straightforward manner by seeing the above example. So it will be e power minus 4s by s square minus e power minus 7s by s square. So Laplace transform of f of t is equal to e power minus 4s minus e power minus 7s by s square. So you can check which option is correct. So I think option number C, option number B is correct. Option number B is correct. So coming to the next problem, work out the inverse Laplace transform of f of t, where f of s is given 2s plus 7 by s plus 3 to the power 4. So let's here find also f of 1. So we wish to find the inverse Laplace transform of this function. So let's write out that f of s is 2s plus 7 divided by s plus 3 to the power 4. So that is equal to 2s plus 6 by s plus 3 to the power 4 plus 1 by s plus 3 to the power 4. So here if you taking common as s plus 3, the remaining part will be 2 by s plus 3 to the power 4 plus 1 by s plus 3 to the power 4. So 1 s plus 3 cancels out, the remaining is 2 by s plus 3 to the power 3 plus 1 by s plus 3 to the power 4. So here we can assume that we know that the Laplace transform of t to the power n is equal to n factorial by s to the power n plus 1. By seeing this formula, we can predict which Laplace transform this Laplace transform and its inverse will be which function. We can predict by seeing this formula. So and another formula is if f of s is equal to Laplace transform of f of t, and we know that from the translation properties of Laplace transform of e to the power at into f of t is equal to f of s minus a. By seeing these two formula, we can infer what will be the initial function of the above. So and the Laplace transform of e power a t to the power s will be equal to n factorial by s minus a n plus 1. So the inverse Laplace transform of 1 by s minus a to the power n plus 1 is equal to e power a t to the power n by n factorial. By using this formula, we can find what will be the inverse Laplace transform of 2 by s plus 3 whole cube plus 1 by s plus 3 whole 4. So here, if you apply the Laplace transform to the inverse Laplace transform to f of s, we'll get 2 into inverse Laplace transform of 1 by s plus 3 to the power 3 plus inverse Laplace transform of 1 by s plus 3 to the power 4. So we'll get what? So this is the Laplace transform of e power minus 3t square by 2 factorial, and plus this one is the Laplace transform of e power minus 3t cube by 3 factorial. So here then f of t will be Laplace transform of inverse Laplace transform of f of s is equal to e power minus 3t square by 2 factorial into 2, that's cancel out, plus e power minus 3t cube by 6. So we'll get e power minus 3t square plus e power minus 3t cube by 6. So again we have to find f of t at t equal to 1. So in the place of t we can substitute 1. We will get, after substitution, we will get 7 by 6 e cube. So we can check which one is correct. So option number C is correct here. Next problem is work out the inverse Laplace transform of the function f of s, which is equal to 1 by x square into s plus 3. See how we can compute this. So here the given function f of s can be written as f1s into f2s. So here f1s is 1 by s square and f2s is 1 by s plus 3. So by seeing this, you can apply various properties of Laplace transform. Here also we will see which property we will apply here, so that we will easily get the solution to this problem. So here f1s is 1 by s square, f2s is 1 by s plus 3. So the inverse Laplace transform of these functions are, let's say f1t is inverse Laplace transform of f1s, this is t, and f2t is inverse Laplace transform of f2s, which is e power minus 3t. So we know the convolution properties of the Laplace transform. So the inverse Laplace transform of the product of two function equal to the convolution of inverse Laplace transform of the two functions. That means the Laplace transform of inverse Laplace transform of f of s is equal to inverse Laplace transform of f1s dot f2s, that is equal to the inverse Laplace transform of f1s convolution of f2s, which is equal to f1t into f2t. So this is the convolution, and how we define this convolution as integration from 0 to t f1 tau f2 t minus tau d tau. So if we substitute 0 to t tau e power minus 3 t minus tau d tau. So after the integration we will get by parts integration we will get e power 3t, then tau e power 3 tau by 3 integration limit 0 to t minus e power 3 tau 9 over 9 limit from 0 to t. So next we will solve this by substituting the limits. This will be t e power 3t by 3 minus e power 3t by 9 plus 1 by 9. So again doing the as inverse Laplace transform of f of s is equal to e power minus 3t plus 3t minus 1 by 9. So this is the answer. So we can see which option is correct. Here option B is correct. So coming to the next problem, here it's given a differential equation. So and initial value condition is given. We need to find the correct answer for y at t equal to pi by 4. So when we saw the one example how to solve this differential equation in the previous session, so here we will just do the Laplace transform of both sides, and then we will see how the Laplace transform of second order derivative, how it looks like. Then we will find the inverse Laplace transform. So let's see how we can do it. state the formula for the Laplace transform of derivatives. Let's say Laplace transform of nth derivative is given as s to the power n Laplace transform of f of t minus s to the power n minus 1 f of 0 minus s to the power n minus 2 f first derivative at 0 simply up to f n minus 1 0. So here it's given the second derivative, so accordingly we will put in this formula. So let's see how it looks like. So let Laplace transform of y t is equal to y capital Y of s. So the Laplace transform of dy by dt is equal to s Laplace transform of y at t minus y 0, which is equal to s y s minus y 0. So Laplace transform of the second order derivative dt square is equal to, again using the same formula, x square l y t minus s y 0 minus y prime 0, this is equal to x square y s minus s y 0 minus y prime 0. On taking the Laplace transform of both sides of the differential equation, we will get that Laplace transform of t square y by dt square plus y is equal to Laplace transform e power minus 2t sin t. So again substituting x square ys plus ys is equal to 1 by x square plus x square plus 1 s 1 by s plus 2 whole square plus 1, just because Laplace transform of e power minus 80 sin bt is equal to b by s plus a whole square plus b square. So y is 1 by s square plus 1 by s plus 2 square plus 1, which is equal to y1 is y2 is. So where y1 is equal to 1 by s square plus 1 and y2 is equal to 1 by s plus 2 square plus 1. So the inverse Laplace transform of these functions are, let's say y1t is equal to inverse Laplace transform of y1s is equal to sine t, and y2t is equal to inverse Laplace transform of y2s, which is equal to e power minus 2t sine t. So the inverse Laplace transform of the product of two functions is equal to the convolutions of the inverse Laplace transform of the two functions, as we see in the previous example. So here yt will be inverse Laplace transform of ys, so that is equal to the inverse Laplace transform of y1s, y2s. So on simplification, that will be inverse Laplace transform of y1s into inverse Laplace transform of y2s, so that is equal to convolution of y1t, y2t. So we know how to define the convolution of two functions. So that is equal to 0 to t y2 tau y1t minus tau d tau. So again on substitution, integration from 0 to t e power minus 2 tau sine tau to sine t minus tau d tau. Then if we do the integration using by parts, so I am stating the direct solution for it, so you can integrate the integration by parts. So this, after the integration, you will get 1 by 2 e power minus 2 tau by 4 into sine of 2 tau minus t minus cos 2 tau minus t 0 to t plus cos t by 2 to e power minus 2t minus 1. So you will get, after the substitution of limit, 1 by 8 e power minus 2t sine t plus cos t plus sine t minus cos t. So therefore the solution for the initial value problem is, in the place of yt, you just simply substitute t equal to pi by 2, t equal to pi by 2 in this formula. In this solution you will get, that will reduce to e1 plus e power minus pi by 8. This solution is a bit lengthy, but this one is very simpler one. So the option number B is correct. Coming to the next problem, evaluate the integral 0 to pi sin x delta double prime x minus pi by 2 dx. So This part of the problem is basically on the Dirac delta function. So we know just now we looked that the sum of the properties of Dirac delta function. So we'll state the properties. Let's say the nth derivative of the Dirac delta function, limit from c to d. Let's say phi of x delta of n x minus a dx is equal to minus 1 to the power n phi to the power n a if a belongs to c to d and it's 0 otherwise. So we have 0 to pi phi of x delta double prime x minus pi by 2 dx. So it will be phi double prime with pi by 2. So it's given phi of x is sin x and phi double prime x is minus sin x. That's simply phi double prime at pi by 2 phi by 2 is equal to minus 1. So the solution to this problem, integration from 0 to pi sine of x delta double prime x minus pi by 2 dx is equal to minus 1. So here the option number C is correct. Coming to the next problem, evaluate the integral integration from 0 to infinity sine square x delta of x square minus pi by pi square by 4. So let's evaluate this integral using some of the properties of delta function. So we know that delta of x minus a x minus b is equal to 1 by a minus b naught delta of x minus a plus delta x minus b. So delta of x square minus 5 square by 4 is equal to delta of x plus pi by 2 x minus pi by 2. So that is equal to 1 by pi delta of x plus pi by 2 plus delta of x minus pi by 2. So using above equation in the integral, so we can evaluate integral from 0 to infinity phi of x delta of x square minus pi square by 4 dx is equal to 1 over pi. It is 0 to infinity pi of x delta of x plus pi by 2 dx plus 0 to infinity pi of x delta of x minus pi by 2 dx. So now we will see that 0 to infinity phi of x delta of x plus pi by 2 dx is equal to 0 to infinity pi of x delta of x minus pi by 2 dx. This is equal to 0. So then phi of x delta of x minus pi by 2 dx is equal to pi by 2. This because pi by 2 belongs to 0 to infinity. So integration from 0 to infinity sine square x delta of x square minus pi square by 4 dx is equal to 1 over pi sine square pi by 2. So that is equal to 1 by pi. So coming to the next problem, so solve the system of differential equation which is dx by dt is equal to 2y and xt plus dy by dt sin t. X at 0 is equal to 0, y at x equal to 0 is 1. So using the Laplace transform, mark the all correct answer. So we can do one thing. Let Laplace transform of f of xt is equal to xs and Laplace transform of yt is y at s So then the Laplace transform of derivatives will be Laplace transform of x prime t is equal to s x t minus x0 which is s x s and Laplace transform of y prime t s l y t minus y0. So that is equal to s ys minus 1. So on taking the Laplace transform of the given differential equations, we will get Laplace transform of x prime t is equal to 2 L y t. So which is equal to s xs equal to 2ys, that is equal to ys equal to s by 2xs. We got the correlation between x and y's. Then the next we can do is xt, Laplace transform of xt plus L yt, y prime t is equal to Laplace transform of sin t. So here we will get xs plus sys is equal to 1 by s square plus 1. Then what we will do is, let's say 1 plus s square by 2 xs is equal to 1 by s square plus 1 plus 1, because y at s equal to s by 2 xs. So from this we will get xs is equal to 2 by x square plus 1, so that is equal to ys s by 2 xs s by s square plus 1. So by taking the inverse Laplace transform of xs and ys, we can find the solution of the given system of differential equation. So here we can find xt is equal to Laplace inverse transform of xs, that is equal to 2 sin t. Here yt is equal to Laplace inverse transform of y is cos t. So then therefore xt is equal to 2 sin t, and yt is equal to cos t. Now coming to the last problem, solve the differential equation. That's dx by dt plus dy by dt equal to 2e power t dx by dt minus dy by dt, 2x minus y, x at t equal to 0 is 2, y at t equal to 0 is 0. So again we will do the same procedure. Let's see how we solve this problem. So here Laplace transform of x prime t minus Laplace transform of y prime t is equal to 2 into Laplace transform of x t minus Laplace transform of y t. So implementing the formula for Laplace transform of derivatives, so we'll get sx s minus x 0 minus h y s plus y 0 is equal to 2 into x is minus y is. So here y is equal to x is plus y0 minus x0 by s minus 2. So again, Laplace transform of x prime t plus L of y prime t is equal to 2 Laplace transform e power t. So from this we will get sx is minus x0 plus sy is minus y0 is equal to 2 by s minus 1. On substituting the expression for y, is in terms of x is and after the rearrangement we will get x of s is equal to 1 by s minus 1 minus 1 by s plus x0 minus y at x equal to 0 by 2 1 by s minus 2 plus x0 plus y0 by 2 1 by s. So on taking the inverse Laplace transform of x's and y's, we get xt is equal to inverse Laplace transform of x is equal to e power t plus x0 minus y0 divided by 2 e power 2t plus x0 plus y0 divided by 2 minus 1. So then we will get yt is equal to inverse Laplace transform of y is. So here in the place of inverse Laplace transform of y is, we will just simply put y inverse Laplace transform of x is plus y0 minus x at 0 multiplied with inverse Laplace transform of 1 by s minus 2. So that is equal to x of t plus y at 0 minus x at 0 into e power 2t. So on substituting x0 equal to 2 and y at 0 equal to 0, so here x of t is e power t plus e power 2t. And we will get yt is equal to xt minus 2 e power 2t is equal to e power t minus e power 2t. Therefore xt is equal to e power t plus e power 2t, and yt is e power t minus e power 2t. So again substituting at x equal to t, x at t equal to 1, we will get e power 1 plus e power 2 equal to e plus e square, and for y at x equal to 1 will be power 1 minus e power 2. If we look at the options here, option C is correct. That brings to end to the session, so you can try as many examples. So basically this Fourier Laplace transform is very much useful in solving the initial value problems at the differential equations, and in future you will appear the various uses of the Dirac delta functions.